In this tutorial, I'm going to talk about 3D graphics with Gideros. Let's start by creating a new project. I'm going to call my project Crate. Let me browse to a place to put it. I'm going to put it in Gideros, and within that, in the folder called Examples. Select folder. So because of this setting, Gideros will automatically create a new directory within Examples called Gideros Examples Crate, and within that it will create a project file called crate.gproj. Select OK. Now we have an empty Gideros project. Let's locate this on the disk drive. And because I'm going to need some graphics, I'm going to copy these from an existing folder. In fact, I just need one graphic. So I put that graphic over here, and that's within my project folder. I now want to add that graphic to the project, add existing file, add the graphic, and now this graphic is available, and this will be a crate, which will eventually become a 3D crate, which we'll rotate on the screen. Okay, I now need to start programming, so I need to create a new source code file, add new file, I'll call it main.lua. Now I can start to write my program. The first thing I want to do is just set the background color to avoid any confusion when we start drawing white objects on a white background. Let me set the background color, and I'm going to set it to gray. So there are 3 channels when I'm drawing specifying colors in Gideros. I specify 3 channels, red, green, blue, within a single number. I'm going to put them all to about halfway up, so 80, 80, 80. It's about halfway, and that will give me a gray background. Let's run Gideros player and play that, and you see I have a gray background. The first thing I want to do is just draw a regular 2D shape, and this will help me later on just to get my bearings in terms of where 3D objects are actually located in space compared to 2D objects. So there's nothing 3D about this so far. I'm just going to create a new shape, and I'm going to set its fill style, and just color it in with a solid color, and that solid color will be red. Let's begin the path. So the first coordinate, the first vertex of this shape will be at -100 by -100 pixels. I draw a line to 100, -100. The next line will be to coordinate 100 by 100, and the final line will be at -100 by 100. Then I can close the path to create a loop, which will be a square in this case, and I can end the path, which completes my shape. Let's position my shape at 120 by 255 pixels. That's where the center will be. And let's set it and let's add it to the stage. So and then we have a simple red square. Now for the 3D stuff. I'm going to create a new mesh, but normally when I create a mesh I would just create it with no arguments. That will give me a 2D mesh. However, if I use the true argument, a single argument which is true, then this will create a 3D mesh. 3D mesh. Now for any mesh I need to immediately start to set its vertices, and I'm going to say the first vertex, index number 1, is at coordinate -100, -100, -100, and finally 100. So these 3D meshes, their vertices have 3 coordinates, x, y, and z. Whereas in a normal mesh you would only have 2 coordinates. So I'm going to say the z coordinate of this mesh point, this vertex rather, is at z equals 100. Okay, let me copy that down and continue. And what I'm going to do is I'm going to create a square, which is going to be the front face of my cube. Now when I'm doing meshes I must only draw triangles. So, but I'll set out the triangles in a moment when I start doing the index specification. To start with, I'll just do the corners of the cube itself. So for the front face, we've got vertices 1, 2, 3, and 4, and these will be at coordinates 100, -100, and z equals 100. So they'll all be at coordinate z equals 100. And then we've got 100, 100. For the x and y, and z equals 100 as well. And finally I'm going to have -100 plus 100, and z equals 100. And those are my coordinates 1, 2, 3, and 4, my vertices, which will represent the front face of my cube. And to remind myself what I'm doing, I'm going to draw a little picture with ASCII art here. So this is a picture of my cube. So you can see the front face is going to consist of the vertices 1, 2, 3, and 4. That'll be the front face. And then at the back of the cube, you've got the other vertices 5, 6, 7, and 8. And they will form the back face of the cube, furthest away from us. So what I've done so far is I've set out the vertex positions of these first 4 corners, which represent the front face, and these all have coordinate z equals 100. To set the back face, it's very simple. I'm just going to copy and paste. And now I'm looking at indices 5, 6, 7, and 8, just as I've drawn it up here. And it's exactly the same xy coordinates, but the back coordinate, the z coordinate rather, will be -100. Let me just line everything up. So now I've defined 8 vertices, which will form the vertices of my cube. I now want to set the color values for each vertex. So when you set a mesh, you can set the color value of every vertex. For vertex number 1, I want to have the color red, solid red. That's solid red, no green, no blue. For the next one, I want to have solid green, no red, all green, no blue, and so on, just so they all look different for now. We don't need to worry too much about which color to use, as long as they're all different. This next one will be solid blue, and this last one is going to be black, so that defines the front face, made of these rather dark colors. When I come to the back face, I'm going to define the coordinates like this. Rather the colors, I'm going to say the colors. So that's full red, no green, full blue, that's going to be magenta. Green and blue will give me cyan. Red and green will give me yellow. That always surprises me. And that's white. Okay, so now we've defined 8 corners of our cube and the colors for each corner. Now, to complete the specification of a mesh in Gideros, whether it's 3D or 2D, I must also specify indices. So I say mesh set index, and now I need to enter 2 integers. And what I'm going to say is the first index will be corner number 1, which is just the, let's zoom out of here. If you look at the ASCII art, in fact I'm going to copy this comment down so we can see it when we're looking further down in the source code here. The first index is going to be number 1, which is this guy, right? Now what I need to do is create triangles, so I need to define 3 indices in a row like this. So index number 2 is going to be number 2, and index number 3 is going to be number 3. So what I've defined is a triangle consisting of point number 1, point number 2, and point number 3, these 3 corners. That will define a triangle, which Gideros will draw for me. To complete the front face, which is a square, it needs to be composed of 2 triangles. So coordinates number 4, 5, and 6 are going to be 1, 3, and 4. If you have a look at that, or 1, 4, and 3 doesn't really matter. So 1, 2, and 3 is that one, and that one. And 1, 4, and 3 is going to be that one, and that one, which specifies another triangle. And those 2 triangles log together to make a square, which is the front face of my object that I'm going to draw. So let's just divide this up a little bit. Let's say this is the front face. So the front face consists of 6 index commands giving me 2 triangles. Right. Let's look at the back face. Let me copy some stuff here. I'm just going to go on 7, 8, 9, 10, 11, 12. So it's a single list of vertices. 5, 6, and 7. You can see why that gives you the back face, right? That gives you one of the triangles in the back face. The other one is going to be 5, 7, 8. So that should be enough for me to see something. I'll see the front face and the back face of my cube. And later on I'll do the rest of the faces. So that should complete the specification of the cube, at least so far. Let's set its position. And I can also set its Z position as well. So set position commands, I can use a Z coordinate as well. I'm just going to set it at 0. This is the entire cube, so it'll be centered on 0. But as we've seen from these coordinates here, its front face will be at plus 100 pixels, and its rear face will be at minus 100 pixels. And so positive Z means closer to the camera, and negative Z always means further away from the camera. That's important to realize. Of course, I need to add the mesh to the stage or I won't see it, which is a common mistake to make. Now, let's see if I can see anything. Okay, well, we don't see anything. The 3D mesh is not displaying anything at all. And the reason for that is I forgot to set the frustum. So whenever I'm doing 3D, I must use this configure frustum command. The first argument is the field of view. For now I'm going to leave that at 0, which will give me an orthographic display. Orthographic display means that things don't get bigger as they get closer, and they don't get smaller as they get farther away. And sometimes it is useful to have this. In scientific drawings you would use an orthographic display, but for games you normally want to have a perspective display, and to do that you simply set the field of view to be something greater than 0. It's an angle in degrees, but for now I'm going to just leave it at 0 and kind of ignore it. The second argument is the distance to the far plane, and indeed to the near plane when it's an orthographic display. So it's a cutoff distance, so anything that's further away than this number in Z will be cut off. I'm going to set it to 200 to make sure it will encompass our entire field of view. So what it means is anything that's further away than Z equals plus 200 or Z equals minus 200, anything that's outside of that range will be cut off. So now that I've done that, if I run that again, now I can see my mesh, which is a cube. But of course I'm only looking at it head on, so I can only see the front face. And you can see the colors are right. So we've got one corner which is solid red, one which is solid green, one which is solid blue, and the other one is black, and you see a sort of gradient effect between them. To convince ourselves that this really is a 3D system, let's just rotate it. Now with 3D graphics there are additional rotate commands. Normally we do the set rotation command, which is rotation in about the z-axis. That's the normal 2D rotation you would do. Of course you can still do that. But you also have these rotation about x and y commands. I'm going to use set rotation to be minus 10 degrees in the x direction, and set rotation, let's say minus 20 degrees, about the y-axis, which is that direction. Okay, now I can see both the front face and the back face of the cube, and it starts to look like it's a kind of 3D object. And you notice the two faces are just the same size, even though one is closer than the other. That's because it's an orthographic representation. It's not perspective mode yet. We'll get onto perspective mode later. Okay, well now I can go ahead and start adding the sides of this cube, the additional faces that I'm going to need. So let's put that up here. Let's carry straight on to index number 13, and it'll be number 7. Let's again copy this down so we can be sure of this. So you can see I'm going to deal with the side which is made of corners 2, 3, 6 and 7. I'm going to do 7, 6, 2, and I'm going to do 2, 7, 3. And you see those are two triangles that make up a square, and that will be the right hand side face. Let me put these in order: 13, 14, 15, 16, 17, 18. So in general you have a large number of indices to set. Okay, and there we can see the side of the cube, so it starts to look more like a real cube. Before going any further, I just want to show the size of this, of the faces of this cube. How big are they on the screen? Because of course we define them to be in 100, but this is certainly not 100 meters or an arbitrary kind of distance like that. It is actually in pixels. At Gideros you always work in pixels and you define positions and sizes in pixels, but what does that mean in terms of a 3D graphic system? What it means is we've defined these vertices to be 100, starting at minus 100 and going up to x equals plus 100, so the total side length of this cube is 200 pixels. But when we come on to setting perspective, that will vary depending on how far away it is. But for now we're in an orthographic state, so if we don't rotate it at all, then the front face of our cube literally is 200 pixels wide. So you are actually drawing things in pixels. And this is different from other game engines, the 3D game engines. In those engines you would typically draw your object in meters, positions and sizes would be in meters. You then position your camera somewhere, pointing at an arbitrary angle, and it draws a scene on the screen, but you would never know how many pixels that scene will occupy actually on the screen. In Gideros you're actually telling it how many pixels wide this thing should be. And because it's orthographic, it doesn't matter how close it is or how far away it is. So to make sure of that, let me do another 2D object, which I'm going to draw in front of my 3D cube, and convince ourselves that this object really is 200 pixels wide. And this is just going to be another shape, so I'm just going to copy this first shape. And this is going to be called shape 2. So everything is just the same actually. So I'm setting up this shape exactly the same as I did with shape 1, same coordinates. But this time I don't want to set a fill style, I want to set it as an outline shape. So if I do set line style, and I'm going to make it 5 pixels wide and black line. Let's set it right on top of where the cube is now. When I'm not rotating it, it's at a certain position. So I'm going to set it the same position as the 3D mesh is. You can see that position is just 150 by 215. I'm going to set my shape right on top of it. I'm going to add my shape to the stage. So you can see that this shape neatly and exactly overlaps the 3D object. Let's try turning on perspective now. Let's have a perspective of 45 degrees and rerun this code. And you can see now that the shape is bigger than 200 pixels wide, right? Although I've still defined it, of course, as 200 pixels wide according to the mesh specification. Because of perspective effects, the front face of the shape is bigger than that, and the rear face is smaller than that. If I put it back to orthographic by setting this to 0, then both faces are exactly 200 pixels wide. Even if I'm in perspective mode, if I, however, set the shape so that the front face is exactly at z equals 0, you can see the front face has a displacement of z equals 100, but if I set the entire shape using set position to be minus 100, then the front face should again be smaller and it exactly occupy this 200 pixel square. So what's happening here is I've pushed the shape back in the z direction. Remember, minus z is always away from the camera into the screen. I've pushed it back, so the front face is exactly at z equals 0 according to these coordinates. So it's minus 100 plus 100. The rear face is at minus 200. We can't actually see that at the moment, but because the front face is at z equals 0, it exactly occupies this square. So what it means is even if you have perspective activated, if an object is at z equals 0, its number of pixels will be exactly what's specified in the vertex specification. So an object of size 200 pixels, which goes from minus 100 to plus 100 pixels, located at z equals 0, will occupy exactly 200 pixels on the screen. If you move it towards the camera, it will get bigger in perspective mode. You move it away from the camera, it will get smaller in perspective mode. But that's the kind of definition of where things are in Gideros. So in 3D shapes, you can always tell how many pixels the shape will occupy if it's right on z equals 0. But if it's anywhere other than z equals 0 and you have perspective mode activated, then the shape might have a different size. Right, so let's put this back at z equals 0. And now because of perspective mode, then of course it looks larger, the front face looks larger than that. Let's try rotating it within perspective mode like this. And now you can see there's a clear perspective going on. The back face is definitely looks smaller than the front face because of the perspective mode that's been activated. If I again turn that back to orthographic by setting the field of view angle to 0, then you can see it looks rather different, very different in fact. And the back face is exactly the same size as the front face. And you can set anything in between. You can set an angle of 20 degrees. That's rather less perspective. And what we had before was, let's say, 30 degrees. And then we take it all the way up to 45 degrees or more, and it starts to look very realistic. And the front face is much larger than the back face. But the other thing to note is that I've drawn 3 objects on the stage, right? One is a shape, a red rectangle. The other one is this black shape, and in between them I've got the 3D object, which is a mesh, and that object is defined like this. But because I added them all to the stage in that order, they'll always be in that order. So whatever the z coordinate of this 3D mesh is, the z coordinate of the cube of any of its corners, it will always be in front of the red square. I can never make it go behind the red square, and it will always be behind the black square, because the normal drawing order of Gideros is things are drawn in the order that they are added to the stage, or to any sprite. So the stage now has 3 children. Its first child is the red square, its second child is the 3D object, and its third child is the black square, and things are still drawn in that order. So if I were to, let's say when I create the mesh, I can immediately, instead of adding it to the stage using add child, I could add child at and put it at coordinate number 1. The 3D mesh will now be behind everything else. Right. And it doesn't matter what the z coordinates of this mesh is, this 3D cube. If I have to bring it all the way up to plus z equals 1,000, let's say, or z equals 100,000, that would be right up to us in our face. Nonetheless, it would still be overlapped by all the other objects on the stage because of this command. And this is very useful because it means I can intersperse 3D objects with 2D objects. So if you're doing a 3D game, you might want the main game scene to be this cube. You might want it to be in the middle, and behind that you might have like a star field bitmap, a bitmap consisting of stars in the sky. Then you've got a 3D shape consisting, which might be a spaceship, but you always want the star field to be behind the spaceship. And in Gideros you can do that just by adding the children in the right order to the stage. You never have to worry about the spaceship accidentally going behind the star field and suddenly you can't see it. Similarly, you'll want a head-up display probably in your 3D game. You want to have some scores shown on the screen. You want to have some controls if it's operating on a touch control device. You want to have some on-screen controls which will always be in front of the entire 3D display. And you can do that by making sure your controls are added to the stage after the 3D mesh, which consists of your entire 3D scene, has been added to the stage. So it's important to realize that Gideros drawing order is still preserved. However, within the 3D mesh itself and its children, then the drawing order will depend on the z coordinates of everything. Now, to make things a little bit clearer in terms of which coordinate is which, I want to add some text fields which will show the number of each coordinate on the screen. And this will also illustrate an important point. So I'm going to do for I equals 1 to 10 do. And what I'm going to do is add a series of text fields. So I'm going to say mesh add child, and I'm going to create a new text field, textfield.new. I'm going to use the default font. I'm not going to bother to create a font. So the first argument is the font you want. The second argument is the text you want, and I'm going to say I. That should be up to 4 only. So what I want to do is have a series of text fields on the screen, which will be at the coordinate of the corner of the corners of this front face. So I'm creating a new text field, adding it as a child of the mesh. Of course, whenever I do that, as with any Gideros objects, children will be drawn on top of their parent relative to the coordinates of that parent. So as the cube rotates, these numbers on its corners will also rotate. Now I want to do something with these children that I've added, so let's get child at I. So as I go through, first of all I add I equals 1, so I'm adding the first child, which is a text string on the screen. I then get access to that very first child, number 1, and I'm going to set its scale to 2, double its size. That's all I'm going to do there. But I also want to position the children. I'm just going to do this one by one. Get the first child and set its position, of course relative to its parent, namely the cube. Minus 120, minus 100 and 100. And similarly. And I'm just going to label the first 4 corners. Okay, so that should be sufficient to see this text fields. Let's have a look. So there you can almost see one of them's gone slightly wrong. Yeah, number 4 should be at y equals minus 100. So you can see I've added sort of labeling to the corners. 1, 2, 3, and 4, which agrees with my drawing here. So the top left corner, number 1, what color does it have? Red, right? Number 2 should be solid green, yep. Number 3 should be solid blue, yep. Number 4 should be black, yes it is. So this is quite useful for illustration purposes. Of course it also shows that I can have any type of Gideros sprite can be added as a child of a 3D mesh. So the 3D mesh itself is this cube that we're drawing, but it can have children as well, and these children are these 4 text fields, 1, 2, 3, and 4. Let's have some fun and set this rotating. I'm going to create a callback called update. And yeah, I'm going to have a global variable called move. I'll define this in a minute. What I'm going to do is I'm going to update the x rotation according to its current rotation. Let's add 0.2. Right, so what I do is I get the mesh's current rotation about the x direction, add 0.2 degrees onto it, and set the rotation to be that value. And let's also make it rotate in the y direction. And add 0.5 in this case. But because I don't want it to just rotate continuously, I want to control whether it will rotate by pressing the keyboard. And I have a global variable called move equals true. For now that will just be true. So I'm just going to let it continue to update. But you'll see why I've done that in a minute. I now need to register this update function with the stage. I need to add an event listener to the stage. So what does it mean? It's an enter frame event. So whenever an enter frame event occurs, whenever the computer redraws a screen, it will dispatch an enter frame event to the stage. That's what I'm telling it. And then it needs to call update whenever that event is received. That means that this function will be called. It will update the x and y rotation of my cube every single frame, so we have an animation going on there. And you can see the whole thing rotates, including all the children. I've only drawn 3 faces of my cube so far. And that's in the orthographic perspective, of course. If I were to change that to a perspective view, you can see how things that are further away look much smaller in this perspective view. Now, as I was saying, for purpose of illustration, I would like to be able to stop this rotation to talk about what's going on. But it's just continuing, so I need to add another function, another callback function, which would be a key down. So whenever a keyboard button is pressed, I want this function to be called. And all this will do is toggle move. So it will say move equals not move. So if move is currently true, move will become false. And if it's currently false, it will become true. So by clicking a button, I can stop things rotating and then restart the rotation again. Once more, I need to register this function, but this time it's not an enter frame event that I'm registering, it's a key down event, referring to the keyboard. And when that happens, I'm going to call key down, function I just wrote. So now over here I can press any key in the keyboard and it stops rotating, and then continue it rotating further. Right, good. Okay, let me proceed to fill in the remaining faces, or at least most of them. Now let's see, we've done the front face, we've done the back face. Let me just copy this one. I'm going to do 1, 5, 8, and I'm going to do 1, 8, and 4. So what I'm doing here, this left hand side, 1, 5, 8, yeah, 1, 5, 8 is one triangle, and 1, 8, 4 is the other triangle of that side face. Let's have a little comment here, separate them out. So I'm just adding more and more vertices and more faces, more triangles and so on to the cube. So now you can see the cube is pretty much filled in, but we can still see through the top and bottom of it. Let's understand this other option within configure frustum. I'm going to put it back to orthographic display, and I'm going to try changing this number and make it less than 100, than 200. Let's make it 50. Now you can see what's happening here is the cube is getting cut off. So there's a cut plane in front of the cube and one behind it as well. So anything that's further away than 50, or closer to the viewer than z equals 50, is cut off. That's the near plane. Anything that's further away from the viewer than z equals minus 50 is also cut off, and that's the far plane. What you'll notice is if you set this first number, the field of view, to be anything other than 0, there is no near plane. So we can see everything in the front, but we still get the back part cut off according to 50. This number z equals 50. So the near plane only exists for the orthorhombic case. For the perspective case, where you have field of view equals more than 0, then you can see everything right up to the camera itself. Okay. So let's increase that again back to a large enough number so that nothing is cut off at all. Now we can see everything, and we can see inside the cube. I now want to have a look at using textures on these faces. So to do that, I'm going to make use of this box. which is a ping file, and I'm going to make use of that and draw it on the various faces of this cube. Of course, being able to draw the cube with solid colors is also useful, let you create interesting graphical effects, but it's also good to be having something that looks like a real 3D crate or other object. So texturing is very important, of course. To do texturing, I need to add a texture or set the texture of my 3D mesh. And this also works for 2D meshes, of course. You can also set a texture for 2D meshes. I'm going to create my texture, texture.new, from this file box.ping. That doesn't do anything in its own right, but it just tells Gideros if you do draw some textures, this is the texture to use. Now, in addition to the set vertex and set color commands, I also need to add set texture coordinate commands. Set texture coordinate. So I'm saying for the first corner, I want to have the texture coordinate 0, 0. And for the next corner, I want to have texture coordinate 80, 0. Now you can see, as it says over here, that the box.ping file is 80 by 80 pixels. So what I'm saying is the second coordinate, I want it to be this one. So I just cut out whatever I want from this ping shape. So I might not use the entire shape. In this case, I am using the entire shape. So the top left corner, which is coordinate 1, that's going to be the top left corner of my cube, is going to have texture coordinate 0, 0 corresponding to the top left hand corner of this shape, of this texture. The second one is going to be here, and then the third one is going to be down here, and the fourth one is going to be over here. So it's kind of straightforward, and of course Gideros is very useful in telling me how many pixels there actually are, so I just make use of that number of pixels. So this will be 80, 80, and this last one will be 80, 0, 0, 80. So now what I've done is I've basically decorated the front face of my 3D cube with this texture. There it is. And you can see it has a color tint to it, which might be not be what I want. And the reason for that is I've set these colors. So what it will do is if a color has been set for a vertex and also you set a texture coordinate, then it will do a color tinting effect. So the top left corner, let's see if I just stop that. The top left corner is tinted red, the top right corner is tinted green, and so on. If I don't want to do that, I can set all the colors to be white, or just leave the whole thing out. So if I comment out all of this, all these color specifications, I don't really need them when I'm doing textures. Everything will be white by default. So I'll just see the pure color as appears in my original ping file. And there it is. Now it obviously looks a bit weird in the other faces. And of course the reason is I need to set the texture coordinates for those other faces as well to be something sensible. So let me go to the back side of this cube. The rear face is 5, 6, 7, 8. So let's set the coordinates, the texture coordinates for those corners as well. So that's just going to be a repeat of what I've said. So 5, 6, 7, 8, I'm also going to cut them out from this exact same texture. And in principle, you could have a large texture which contains different appearances for all 4 faces of the cube, and they'd all be laid out flat on this box.ping, like a net view of a cube. But I'm going to reuse exactly the same graphics for all 4 faces. Well, it looks okay for this face. 1, 2, 3, 4, right? And it looks okay for the back face, But what's weird is these side faces. They don't look very good. And the reason for that is, if you look at corner number 1, which is the top left corner, of course, it has a texture coordinate of 0, 0. This corner over here is corner number 5, and it has exactly the same coordinate, and that's fine for the back face and the front face, but this side here has the same texture coordinate here as it has here, and the same one here as it has there, so you don't want to see that. And that's why it looks like these horizontal lines are being drawn instead of drawing a nice picture of the box.ping texture that we wanted. So the way to overcome that is to draw these coordinates in a different order. So if I start with the AT01, which is obviously this corner, this top right corner, then I go 0, 0, then I go 0, 80, and then I go 80, 80. If you look at that, that looks a lot better, right? So you can see the back face is in the opposite direction because I've ordered the texture coordinates differently, and it works in such a way that the side faces also show a pleasing pattern. So basically, you look at the front face, 1, 2, 3, 4, it has the opposite appearance, and this diagonal line, this bar, is being drawn in the opposite direction, which is what we want to happen. So if I allow that to rotate, it's a nice cube. I can see inside, and all 4 faces have a different shape drawn on them. Well, it's the same shape, but it alternates. This bar, this diagonal bar, is going up and then going down and so on. Okay. Now, of course, I want to eventually draw all 6 faces of this cube to make it look really solid. So in principle, all I need to do is draw some more indices to specify some more triangles. I've already got all 8 corners of my cube, right? And I just need to reuse those corners to draw more triangles to fill in these gaps. But we're going to encounter a problem when we do that, but let's fall into that trap and see what happens. Okay, so I'm going to draw one more face. Let's just make a note. This is going to be the top face. It's going to be the top of my cube. Right. So that top. Let's copy this one more time so we know what we're doing. I want to draw the top face of my cube. Mesh. Set. Index. We're up to number 25 now. 25, 9. Not 9, 1. So I want to draw the top face. Is going to be 1, 2, 6, and 5, isn't it? Right. 1, 2, 6 will give me one of the triangles. 1, 6, 5 will give me the other triangle. Okay, so that should draw the top face. Let's see. It has drawn a face, but it looks a bit weird. And you can see it's the issue of the texture coordinates again. And what's happening is that texture coordinate specified there is exactly the same as that texture coordinate specified up there. That's why you're getting these diagonal lines. And there's no real way to overcome this, unfortunately. If I go back to where I specified the texture coordinates initially, I specified the texture coordinates for all 8 corners of the cube in a way which worked very well. But whatever I try to do, however I try to rearrange this second batch, the top face will always be inappropriate. So the only way around this is to create more coordinates. Even though they happen to have the same actual XYZ coordinates in space, nonetheless I need to create more vertices such a way that I can actually define the top face correctly. So sometimes you can't get away with a reduced number of vertices. Sometimes you have to have the full set or nearly the full set. And this is to do with texturing in a correct way. So let me do the top. I'm going to add some more vertices to my mesh. Set vertex, go on to number 9 now, minus 100, minus 100, 100. So let me make a note, this is going to be the top face. And what you can tell from this is it's going to be completely impractical to design a very complex 3D shape yourself using these set vertex commands. What you need to do is have a library which reads in from a standard CAD format or drawing system, an external 3D drawing package, and creates these meshes for you. And if you look through the Gideros examples and look at the horse example in 3D, you will see precisely such a library that reads from a standard 3D meshing format and recreates a 3D shape on the screen. But of course in this tutorial I'm doing everything from scratch, which is sometimes fine. If you have simple cubes and things, then it's certainly possible to do that. But if you're trying to draw a horse or a car, you probably don't want to do that. Alright, top face, second coordinate 100 minus 100. And minus 100. And some of these vertices are repeats of ones you've already seen. So that first one, that number 9, is exactly the same as number 1. Right, same XYZ coordinates. But I need to repeat it because I need to set one of its attributes differently. It happens to have the same XYZ coordinate, but I want to give it a different texture coordinate. And I'll have to do that. So let's finally go on. So we've already done 1, 2, 3, 4, 5, 6, 7, and 8. We've defined the texture coordinates for all those indices. Let's finally do the same thing for the new set of vertices that I've just considered, just added on. These are 9, 10, 11, and 12. And I'm just going to do, it doesn't really matter actually, because this face basically has its own set of coordinates anyway, so it doesn't have to share them with anyone else. I'm just going to use 0, 80, then 80, 0, then 80, 80, and then 0, 80, which is the same as my first face. So now I've set more vertices. I've got a total of 12 vertices, and for each vertex I've set the texture coordinates, all of which are pulled out from this box.ping. Finally, I need to go on and set up the triangles using setIndex command. In fact, I already did that, but not correctly, so what I need to do now, for these final set from 25 to 30, I must set them not to be 1, 2, 6, 1, 6, 5, but I want to set these new vertices that I've just added, which are high-numbered vertices, starting at 9. So I'm going to set 9, 10, 11, and 9, 11, and 12. That should now create this final face correctly. Okay, let's have a look. Does it look good? Well, not quite. Perhaps I've made a mistake here. Yep, it's in my original texture coordinates. Should start at 0, 0 to pull out the top left corner of this box. Let's try that. Yeah. So there I have a nice cube, and of course I can do the final face quite easily in a similar way and generate a fully 3D textured cube. So there are several fundamental principles we've learned today about how to draw 3D graphics using Gideros. Firstly, 3D graphics are specified in pixels. So if we set, let's get it running, if we set the mesh vertices so that the object is 200 pixels wide, then it will be actually 200 pixels on the screen if the object is at z equals 0. If it's closer to the user than z equals 0, that is, if z is a positive number, then it would be bigger than 200 pixels in this example. And if z is a negative number, then it will be smaller than 200 pixels. And how much bigger or smaller it gets depends on the field of view, which we set using the configure frustum option. If we set the field of view to 0, which is the first argument, then we have an orthographic display, in which case objects are always at the same size however far away they are from the camera. And then everything will always be exactly the number of pixels you specify in these set vertex arguments. The other thing to realize is that 3D objects, when we define a 3D object using mesh.new true, it still fits within the normal 2D drawing system of Gideros. So in this example, the red square was added first, is the first child of the stage, the second child of the stage is this 3D object, and the third child is the black square. And these are still drawn in that order. So 3D objects like this new mesh, mesh.new true, still fit within that drawing scheme. However, within the mesh.new, the 3D mesh, then any children of that mesh will not be drawn according to the order that they were specified, but rather according to the Z order. So any objects that are further away will be drawn first and will be overlapped by objects which are nearer, irrespective of the order that these children were added to this mesh object. In terms of where the camera is, Gideros has a fixed camera which is always looking into the scene. The camera is located right in the middle of the stage. In terms of the XY coordinates, its Z coordinate is given by this formula, which you'll see on the screen now. So it depends on the field of view. If the field of view is very small, then the Z position of the camera is a very large distance away in the positive direction. And if you have an orthographic display with a field of view equal to 0, the camera is at infinity. You can never actually get up to objects and move around them. So in a realistic game, you probably always want to have a perspective view. But the point is the camera is fixed in the center, it's fixed at this Z coordinate that I specified. So if you want to have a scrolling game where you're walking in to a scene and moving around all these objects, you have to move the objects towards the player rather than moving the player towards the objects. So you don't have a movable camera in Gideros. Rather, you have a fixed camera that's always pointing in the same direction, and you have to move objects around that way. And it's the same for Gideros even in 2D games. So if you have a 2D scrolling game in Gideros, and the hero character is in the middle of the screen, everything is moving past him, then you have to make everything move to the left to make it look as though the character is moving to the right. There's no camera that can follow the character, rather you have to move all the objects in the opposite direction.